Okay, so let's get started. We will continue today to talk about medium access control. Medium access control is methods for multiple users or multiple stations to use a common medium. So to negotiate access to the medium. So a few slides on review here when it comes to notation and changes from earlier. So the notation now is slightly different from the ARQ chapter. So now frame duration in seconds is called X, the frame length in bit is called L, and the medium data rate is called R. That's the same, I guess, as before. And that's in bit per second. So that means that the rate which we transmit frames is L divided by X. Okay, so good equations to remember. Now we're talking about the aggregated data rate. So now we're not only considering one single transmitter when we talk about data rate, when it comes to the effective rate and so forth. Now it's the rate from all the users added together. So the total rate on the medium, it comes from all users, not only one users. This is also known as throughput, and notation is RF, R effective rate, bit in second. So the normalized throughput is also called load. So both of these words we will use simultaneously, depending on what aspect we want to emphasize. Variable rho, and that's the effective rate, the user data rates, divided by R. So again, this is the number of bits per second transmitted by all users of the medium. And R is the maximum rate that the medium can support. So the ratio between these two is called normalized throughput, or we can think of that as the load also. Load in the sense that when the effective rate from all the users is increasing, getting closer to R, we are getting closer and closer to the maximum capacity of the medium. So the maximum load supported by a certain medium access control mechanism is called rho max, and that's the maximum rate we can support to all the users. And this depends on the method that we are using, but also on the properties of the medium. And again, we divide through by the rate of the medium. The longest propagation delay of the medium is called T-prop, and it's in seconds. And the normalized delay bandwidth product A is R, the bit rate of the medium, times R, the propagation time divided by L. Or one can think of that as the propagation time divided by the time it takes to transmit one frame. It's the same thing. And then we are talking about the frame transfer time, and that's the time it takes for a frame to be present at the present at the transmitter when it occurs at the transmitter MAC until it's delivered at the receiver MAC. Okay, so it's the time it takes for a frame to be transmitted over the medium. And this in general is a random variable because of delays over the channel, which is because the channel might be busy depending on other traffic which is ongoing. So this is typically a random variable. Okay, now the maximum load, rho max, is a number between 0 and 1. Okay? And it can be interpreted as the best case efficiency also of the medium access method. That's the maximum load the medium access method can provide or handle rather. So we can think of rho max also as some type of measure of efficiency of the medium access control method that we're using. And this differs from method to method. The load rho, which is the load we have at this point in time, that depends a little bit on the current conditions. So we can think of that as the MAC efficiency under current conditions. So rho here will be less than rho max, it follows naturally. Okay, so this is the best we can do, best in terms of efficiency, the highest load we can do. Rho is the load we are using at this particular moment. So it could be fairly low, for instance, and then efficiency will also be low, but that might not necessarily be a problem. Because rho here will scale with the demand also. So if the demand is low, then the load is low, but we are able to serve all the users anyways. So that's not necessarily a problem. Okay, so hopefully this was clear. Now, coordination of a medium explicitly or implicitly needs bandwidth. That is, we need to use the medium in order to coordinate access to the medium. So this is the main problem. We don't have a magic scheduler or somehow that tells us what to do. We need to negotiate access over the medium. So this difficulty of coordination increases with this delay bandwidth product that we talked about on the previous slides. And the frame transfer time also typically increases. And the frame transfer time typically increases as the load increases. So as we're getting closer and closer to our maximum capacity or maximum load, we get more and more delays in the system typically. And that seems to be natural, right? We need to wait longer to access the channel, and therefore delays is increasing. So we talked about random access last time. We talked about ALOA, and we will talk about slotted ALOA a little bit later today. ALOA is the simplest thing we can imagine. It's very close to stop and wait ARQ. That is, at the transmitter, whenever a frame is requested to be transmitted, okay, so what happens here? I'm the medium access control protocol, I'm ALOA. So I get a frame from above, and what I do is I just send it. Okay. And then I send it, I start a timeout counter, and then I wait for an acknowledgement. If there is no acknowledgement before the timeout expires, I retransmit it. Okay. And I keep on doing that until I get an acknowledgement. When I get an acknowledgement, I can accept the next frame from above. So while I'm in retransmission, waiting for the ACK, then the upper layer is blocked. So I cannot transmit any more frames. So I transmit one frame at a time, but the access to the medium is quite aggressive. As soon as I get a frame, I just transmit that, regardless. Okay, regardless of the state of the medium. Okay, now we did a quick tour into some math, because what we want to do now is to model how frames are arriving for transmission. So if I'm the medium access control layer here, I get frames from above. How do I get them? Do I get them regularly, or do I get them at random times? So for analysis, we typically model the arrival times, that is frame arriving from above, as a Poisson data traffic, which means that they arrive at a certain rate, but not at a constant rate. So every now and then I can get a lot of frames, and every now and then I don't get a lot of frames. On the average, however, there is a certain rate. So the time between frames I get, if I can model that as an exponentially distributed random variable, I have this Poisson data traffic. So it's quite a common model for this. So the probability mass function for this is characterized by this lambda, which is the intensity. So if y is a Poisson random variable with variable lambda, intensity lambda, that means that under a certain time unit, there will be a number of events, a random number of events, and the number of those events is characterized by this random variable y. So the probability that y is equal to k, that is that exactly k events happened during my time unit, follows this equation. Okay? So now the probability that y is equal to k is given by this, and it's characterized by this lambda. And the expected number of events during a time unit is lambda. Okay. So that's why it's called the intensity. So for instance, if y is the number of frames I get from the upper layers, if lambda is equal to 1, that means that I get essentially 1 frame per time unit. If lambda is 0.1, it means that I get approximately 0.1 frames over 1 time unit. This time unit time period could be 1 second, 1 minute, 1 hour, or as we will see later on, normalized to the frame duration, the time it takes to transmit the frame, because that's convenient to us. Okay, so the intensity lambda here could be frames per second, frames per minute, or frames per frame duration. That is, number of new frames we get per frame duration. And the frame duration could be, a couple of milliseconds maybe, depending on the data rates and so forth. Okay, now an important thing is that if z is Poisson with lambda 2 and y is Poisson with lambda 1, then w, which is y plus z, is also a random variable, and that turns out to be a Poisson with a intensity which is the sum of the intensities of the individual random variables. So this is quite useful. So if we have Poisson traffic from 2 sources and I aggregate them to one source, then that source will have Poisson data traffic, but with the sum of the rates. Okay, so it's quite convenient to us. Okay, now ALOA. So we know what ALOA is. It's basically this. So how can we say, is it any good? Then we need to do some calculations. And what we would like to do is to calculate, for instance, what is the maximum throughput we can get, what is the frame transfer delays, and so forth. So we will do this a little bit simplified here, because the analysis in its full detail is quite complex, I would say, and not always well understood. So we'll do a few assumptions here that will allow us to say something about ALOA, and that what we say will actually be quite robust. So will actually be what we can see in reality. So we say that all frames have the same duration. Okay, so that's quite a simplification. So all the users are sending frames of exactly the same length, x in seconds. And during x seconds, there is a number of new frames arriving for transmission. So we have a bunch of stations. All of them are listening to their upper layers, and they get frames from above. The aggregated rate for all stations attached to the medium is lambda n. Okay, so within one time unit, on the average, lambda n new frames are generated for transmission. Okay, so the number of new frames generated for transmission is y, and this is for all frames for all stations attached to the medium. So it's not per station; it's for the whole system. The number of old frames which are scheduled for retransmission is called z. And we assume that that is a Poisson random variable with some rate, lambda r. So at any given point in time, there is a number of frames being requested to be transmitted, and that's the sum of new frames plus frames which are scheduled for retransmission. Okay, so there is a rate here, g, or w is the number of frames that are the frames that are to be transmitted. Okay, and they consist of new frames and old frames. Okay, so here are the frames that are coming to the channel. Okay, and in one time unit we have w of those, and that's the sum of y and z, and that turns out to be a Poisson with some variable g, where g is the sum of the rates here. So the sum of this rate and this rate becomes g. Okay, so we have Poisson traffic coming to the channel here with intensity g. So for any time unit in x seconds, we get g new frames for transmission. Okay. So I take that again. During x seconds, on the average, we have g frames to be transmitted during a time interval of x seconds. Okay, so this goes over the channel, and then two things could happen. Either there is a collision, and then we assume that the frames are lost. So when there is a collision, the transmitter goes into backoff, that is, waits some time before it starts to retransmit again. And then it's fed back and then transmitted at some later time. The other thing that could happen is that the frame is successfully transmitted. Okay, we got lucky, right? Nobody else was using the channel when we transmitted the frame. And then that happens with, on the average, with s frames per x seconds. Okay. So once more, lambda n is the rate of new frames. Lambda r is the rate of frames that are scheduled for retransmission. G is the rate of frames arriving to the channel. S is the rate of frames leaving the system, meaning that they are successfully delivered. Okay. So we have this feedback thing here. So if we start with a very low rate, most of the frames go through, right? Because there are a few collisions. However, when we crank up the input rate here, there will be some collisions, and then we increase the rate here. So we have positive feedback, which means that we could end up in an overloaded situation. And what to do then is either to reduce the input rate so we are not transmitting as fast as we would like to do, or we increase the back-off time, which means that the rate of back retransmissions here will be reduced. This will become a little bit clearer later on when we look at these type of strategies later. Okay, but anyways, if we are in steady state, so we put in some frames here, and everything is oscillating and then converging to some steady state, some equilibrium, then at equilibrium, when things are not dynamically changing, that these rates are changing. Because when we put in a rate here, there will be some feedback here, and it takes some time before this converges. But at equilibrium, then the output rate, S here, must be the input rate, lambda n. Otherwise, we would, this feedback would just build up this higher and higher and higher. Okay. All right. So now we are ready to calculate then what is the throughput for LO1. And the general approach is as follows. And let's go through that in some detail. Okay, so now if we go back here, at some point there arrives a frame to be transmitted to the channel. Okay, so let's consider that event. So suppose a frame is transmitted, or we will use the word arrives. Arrives mean that it arrives to the channel to be transmitted. So okay, so arrives and transmit is the same thing here. At some time t0. Okay. So if we have our time axis t here, at some point in time t0, a packet arrives for a frame arrives for transmission. So it is transmitted then during a time interval of x seconds. So the frame duration in time is x seconds. Okay. So this is the transmission which is ongoing. So will this transmission be successful or not? Well, that depends whether there are other frames arriving at the channel during a certain time interval. So we see all frames which are arriving later than t0 plus x will not interfere with the channel. So those are okay. But arrivals which are previous to this frame will interfere with this frame if the arrival is within the interval from t0 minus x to t0, right? Because then this will interfere, this arrival, right? Because then that frame will leak into the frame that we are trying to transmit at this point. Okay, however, if the arrival is here, that's okay. Instead of interfere, maybe we should say collision. Okay, So I hope this is clear now, that if we are transmitting a frame with start at t0, then if there is a arrival to the channel within the interval from t0 minus x up to t0 plus x, then that frame will interfere with the frame that we are trying to transmit. Is that okay? Right. So arrivals that occurs between this time and this time will be very harmful. So we call this the vulnerable period. Okay. So if we are transmitting a frame here, any arrivals within this time interval here will cause a collision. Okay, so what is the probability that there arrives one or several of these that cause a collision? We can turn the thing around. What is the probability that there arrives no frames over a time duration which is equal to 2x seconds? Okay, so this is 2x seconds long. Well, we know that the arrival rate to the channel here is g. Okay, so on the average, g frames are generated every x seconds. So how many frames on the average is generating during 2x seconds? It's not hard, actually. So if g is generated for x seconds, how many on the average is generated over 2x seconds? 2g, right. So the arrivals over, okay. The number of interfering frames during 2x seconds let's call that v, is a random variable, and it's Poisson with rate 2g. Okay. Okay, so the probability of no collision, what is that? Well, it's the probability that it generates exactly 0 frames during a time period of 2x seconds, which is the same thing to say it's the probability that v is equal to 0. And since v is Poisson distributed, this is 2g to the power k divided by k factorial times the exponential of minus 2g. Is this correct? Let's see now. Yes. When k is equal to 0. Okay, so this is the probability that v is equal to k, this k, and then we put k equals to 0 because we want to calculate the probability that v is equal to 0. And this is quite simple then. 2 to the 0 is 0. 0 factorial by definition is equal to 1, so the first term here disappears, and the only thing we are left with is the exponential. So now we know the probability that there will be no collision for a frame that we transmit, and that is e to the negative 2g. Okay, which means that if G increases here, we see that the probability for success becomes smaller and smaller, which should be the case, right? Because the more frames we have to transmit, the more likely we have collisions. Okay, so now what is the throughput? Well, transmission attempts are done with the rate G frames per x second. Okay. So we are transmitting frames. We are transmitting these frames with the rate G frames per x second. Okay. So then the throughput will be G, the number of events, the number of attempts we do, multiplied with the probability that it goes through. That will be the throughput. Okay. First of all, the success rate will depend on the attempt rate. So G is the number of frames that we attempt to transmit per x seconds. S is the number of frames that we are actually getting through. Okay, so these are less than G, right? Because some of these will be colliding. Okay, so the success we get is G times the probability of no collision and that is, we just calculated that the probability of no collision to be e to the negative 2g. Okay. So this is the throughput we can get for ALOA. Okay. So S here depends on G through this equation, that S is equal to G e to the negative 2G. Okay. What is G? G is the rate which we access the channel, and the rate depends on the rate of new frames coming from above, from the protocol layer above, plus those who are scheduled for retransmission. So G here is not all new frames, it also includes retransmissions. Okay. All right. Now, we will see a graph of this very soon, but we see here, what can we do in order to improve the throughput of ALOA here? Well, the thing is that we see that all frames which are generated through the vulnerable period would lead to a collision. So can we reduce the number of frames which would lead to this? We could do that by enforcing access to the channel to happen at regular times. That is, we introduce some type of time slotting here, or slotted access. So what is meant by that? Well, we divide the time access into slots. Okay. And a frame or a transmitter can only start its transmission at the slot boundaries, not at arbitrary times, but only at slot boundaries. So a transmission can start here, 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 or here, never in the middle. Okay. Now, suppose that station A is transmitting a frame here, it takes X seconds to transmit that. And then it propagates over the medium. And then it reaches the furthest away node within a certain time, which depends on the propagation time over the medium. Okay, so for a large medium, this time will be larger. For a smaller, it will be smaller. So if we let the slot length be X plus some guard interval to take into account the propagation time here, we can see that a certain frame is only confined to one slot here. It would never go into two slots. And by doing that, we reduce the possible damage this frame can do in terms of collision, because this green frame can only collide with frames which are in the same slot. Okay. So B here, for instance, when it transmits its frame, it will pass through the medium like this, and here for C and so forth, and we can keep on going like this. Okay, there are no collisions here. Okay, so the guard interval here needs to exceed the largest propagation delay plus some margin for synchronization errors where we don't know exactly where the boundary of the slotting is. But suppose we can now enforce this slotting here. Okay, for efficiency reasons, of course, X here needs to be much larger than the guard interval. Okay. I hope that's pretty clear, I hope. Okay, now if we do this slotted and we ignore the guard interval, so the assumptions are the same as for unslotted ALOA, and the guard intervals, we assume that they are negligible compared to X, so we can ignore them in the analysis here. Then the vulnerable period for, suppose we want to transmit this blue frame here, then collisions with this will only be those frames which are generated during X seconds. Okay. All right. So now the vulnerable period is X rather than 2X as we had before. Before we had that frames which were generated during a period of 2X seconds will cause a collision. Now, only frames that are generated during X seconds will cause a collision. So the collision rate goes down with a factor of 2. Right? So the probability for no collision is now e to the negative g instead of e to the negative 2g. Okay. So that's the only difference. The attempt rate is still the same g. Okay, so now this is throughput for slotted ALOA under these conditions, of course. So is this any good? Well, let's see now. So this is the summary slide of ALOA, right? So this is quite important. So if we understand this, we understand quite a lot about ALOA. So on this vertical axis here, we have the throughput, S. And remember, S is the number of frames that go through the channel during X seconds, where X is the time it takes to transmit one frame. So S here is a number less than 1, has to be. Okay? Because we cannot transmit more frames than continuously transmitting non-colliding frames on the channel, and then S will be equal to 1. So S will always be less than 1. G here is the attempt rate, the rate with which we are trying to transmit, the rate which we are transmitting frames with. Not all of those goes through. These are the frames that go through, and these are the frames that are transmitted. Okay. So from a rate perspective here, we have a rate of new frames. We have a rate of frames which are scheduled for retransmissions. Together they form G. Out of G, a fraction, S, gets through. Okay? The other ones goes back here and then adds to G. Okay? So as we increase G here, we get more and more attempts to the channels, we get more and more collisions, and we would expect that throughput goes down. If G is very small, we would expect no collisions, and then S would be equal to G, more or less, in this region. Okay. And that's exactly what we see. So if we go through slotted ALOA, for instance, then the throughput, our analysis showed this, and then this is the red curve for this. So in the beginning, the slope here is essentially 1, which means that all attempts are successful. Then we are getting more and more collisions, more and more collisions, more and more collisions, and here we get the maximum throughput we can get. Okay, but and that happens when G is equal to 1. When the number of attempts on the average is 1 per frame duration. Sort of makes sense, right? Then if we are greedy and increasing this, then our throughput goes down. Down, 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 and eventually goes down to 0. And then we are only generating collisions and nothing else. Nothing gets through. So any new frame that goes in here just goes around here, right? It never pops out here. Okay. So for small g, S and G are approximately the same. For large G, S goes to 0. At equilibrium, the throughput is equal to the new frame rate. So at any point on this curve, if we are stable here, so we're not moving up and down due to the dynamics of this, then this is, S here is also the rate that goes in. So S and lambda is the same in equilibrium. Okay, now, so we are interested in maximizing throughput, and we do that by pushing in more and more frames into the system until we peak here. Okay, and the peak occurs for normal ALOA at a arrival rate here, which is 1/2, and then it's 1/2e, which is roughly 18%. Okay, so with unslotted ALOA, under best conditions, if we want to maximize throughput, we get about 20% of the slots or attempts are successful. Okay. So during a time of x seconds, we are getting 1/2e frames through. Okay. So x seconds, we get approximately 0.18 frames through. The next x seconds, we get another 0.18 frames through. Even though, if we had perfectly scheduled this, we could transmit 1 frame here and 1 frame here with no collision, if we had perfect synchronization, coordination. Okay. So this is quite low, but that's the price we have to pay for having this type of loose coordination. If we enforce slotting, we get double this. So for slotted, the maximum throughput we can get is 1/e, which is roughly 37%. Okay. So with slotting, we get double the maximum rate. Questions? Okay. I know from experience that this takes a little bit of thinking and pondering before the ideas falls into place. So please give this some time when you read up on it. And don't hesitate to come and ask later on. Okay, now, can we do better than ALOA? Better than slotted ALOA? Yes, we can. So, for instance, it's maybe clearer here. Suppose I'm a station that wants to transmit this frame. Okay. In ALOA, as soon as the frame comes from above, I start to transmit that, regardless of what's going on onto the channel. Right. Can we do better here? Yes, we can, because if I, at this point in time, listen to what was going on to the channel, I would see that there was a frame in transmission already. So instead of transmitting my frame, I could essentially wait until this frame is done, right? Because I know if I hear that the channel is busy, I know I'm going to cause a collision if I transmit. So why should I? Right? So this is the general idea between with what's known as carrier sense multiple access. It's a listen before you talk protocol. It makes perfect sense. So what do? We sense the channel, which is listen to the channel. If the channel is idle, that is, we don't hear any ongoing transmissions, then we assume that the channel is free, and then we transmit. If the channel is sent as busy, then we need to wait, right? And here there are different techniques for how to wait, different approaches. So we wait until the channel is idle, or we back off, and we will see a few of these examples very soon. Now, if a collision is detected, then we back off and try again. And a collision could be detected in the sense that we don't get an acknowledgement from the other side, or we can actually maybe also listen to the medium when we are transmitting also. So how could there possibly be collisions? Well, it could be because we have propagation delays. So for instance, suppose that station A is start to transmit a frame here. So A listens to the channel, is free, and here a request comes for transmission. So the station A gets a frame from the layer above, it listens to the channel, it's free, good, transmit. Okay. And then it transmits, and then it propagates over the medium. Now, station C is also listening to the medium, and the medium is free during this time, even though it's actually busy, because a frame has already been started to be transmitted here. But C has no idea or no way of knowing this. So C here, during this vulnerable period, this is called also a vulnerable period, it's the time where sensing the channel does not give the accurate result. That is, we can see here things that everything is okay and could start to transmit during this time, and then a collision would occur. Right. So there is a probability for collision, even though you listen to the channel and transmit only when it's free. Right? However, when the frame actually arrives here at C during the blue period here, the period here, then if C senses the channel during this time, it will not transmit. Okay? C will sense here and say it's idle and it's okay to transmit. Here it's blocked, and now it becomes idle again. Okay, this vulnerable period here is equal to the propagation time. Okay, and here when we talk about propagation time, we talk about the maximum propagation time from over the medium. So A is the station which is furthest away from C, and then this is the propagation time. Okay? All right. So what can we do then if we are sensing the channel over this blue period here? Well, then we need to back off, or we need to make a decision on when to sense the channel again and possibly transmit. Okay, and there are three main, actually only two, but say that there are three possibilities. If I'm at station C and I sense the channel here, it's busy. Okay, what can I do? Well, one way to do is to keep on sensing the channel. It's busy, 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 busy. Not busy. If it's not busy, then I transmit. Okay, so this is quite aggressive because station B might also do the same thing. Busy, 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 and it transmits here. And then we will get a collision because these two start to transmit here. So if this is called persistent CSMA, that we listen until the channel becomes idle and then we transmit. Okay. Another thing we can do is that if I sense the channel here and I say, okay, it's busy, then I'll just wait a random time before I start to listen to the channel again. So here I draw a random delay, maybe ends up here, and then sense the channel at this point in time. If it's busy, then I draw another random time and check again. Okay? So this is a more polite way to do things because less collisions will occur. And then there is a third option which is called P-persistent CSMA, where we sense the channel, and when it's free, we don't automatically transmit. We only transmit with a certain probability, which is called P. And then we sense the channel a little bit later. If we don't transmit here, we sense it a little bit later and then transmit again with a probability P. So it's a little bit of a mixture between these two approaches. So what I said in words here, these are the variations of CSMA. We have persistent, non-persistent, and P-persistent CSMA. Let's take a break now.